For this lesson, we're going to have a look at parallel and multi-core processing. But first of all, let's have a reminder about CISC and RISC. This PowerPoint will work best if you run it through as a PowerPoint. So I'm going to read out a statement and I want you to tell me whether it is CISC or RISC. So the complex instructions are built directly into the hardware. Please write this out and then decide if it's CISC or RISC. The compiler has to do more work to convert high-level language, such as Python, VB or C Sharp, into instruction code. Write your answer now. That would be RISC. The primary goal is to complete the task in as few lines as code as possible. Write down what you think it is. And the answer is CISC. Each instruction is executed with one clock cycle. Well, that would be RISC. Remember, some instructions within some process might be more than one clock cycle for each instruction. The processor hardware is capable of understanding and executing a series of operations in one instruction. Well, remember that is CISC, because a CISC instruction has a lot more complex to it and usually has a load and store involved in it. Load and store instructions are needed to be explicitly stated in the program. Well, this is a RISC instruction. We need separate codes for load and store. More RAM is needed to store the instructions. That would be a RISC processor. Now remember that each instruction needs a space in RAM. So if we have more instructions for the same code, then we're going to need more RAM. The explicit loading and storing instructions is not necessary. They're built into codes. Pause and write your answer. This would be CISC. Instruction code closely resembles commands in a high-level language. This would also be CISC. Less transistors are required. Try and write down what you think it would be. The answer is RISC. Remember, the instructions are simpler, so the logic will be simpler, so we need less transistors. The compiler is going to do very little to translate from a high-level language into machine code. Write what you think it is. The correct answer would be CISC. There are a larger number of general-purpose registers. The answer would be RISC. Pipelining is possible, fetching the next instructions, remember, whilst decoding the current instructions and executing them. What do you think it is? The answer would be RISC. They are cheaper to produce. That would be a RISC processor. The length of code for a program is relatively short. That would be a CISC processor. Very little RAM is required to store instructions. This is a CISC processor. Remember that the instructions are all in one in CISC, so you'd have a load and store, so you only need one location in RAM. A simple instruction format can mean faster processing. Which one do you think it is? The answer would be RISC. These are the keywords that you will need to know for this topic. You should know all about CISC and RISC by now. If not, you need to go back and complete this section. We are looking at the section on multi-core and parallel systems. We're going to continue on to GPUs in the next lesson. In the olden days, you'd have one CPU per machine, but as demand has increased, we've changed CPUs, and we've now started using multi-core processors and parallel systems. As you should hopefully already know, a multi-core processor is a single processor chip which could have more than two processing units. If you look at the diagram on the right, you can see that here we have shared cache for 4 different cores. So this would be a quad-core processor. And most manufacturers integrate these cores into a single chip or a single CPU. These are known sometimes as CMPs, chip multiprocessors. They often have shared local cache. This basically means they can access the same data instructions quickly, and they can sometimes have inter-core communication to access this cache. Just remember that if we double the number of cores, that doesn't necessarily mean the processing speed will double. That depends on the software programs that we are using. Nowadays, we have some supercomputers such as the IBM Blue Genie, which has 4,098 processors. This allows us to do a massive amount of processing. And we know that supercomputers are used on problems such as weather forecasting, climate control models, or any big data. We might be analysing DNA sequences. This is really important that we have multi-core processing so that these different cores can process different parts of the data at one go. This improves the performance that we would get from a computer. It gives us the advantage of parallel processing, which means each of the cores can be processing, fetch, decode and execute data or instructions at the same time. So this is maximising our resources. We should know this word already, but parallel processing is the use of multiple cores running the same program in less time. Here you can see an abstraction of what it looks like. Sometimes we can have multiple processors running at the same time, potentially with multiple cores. Again, aiming at running the program in less time. We see this quite often when we have a CPU running concurrently with a GPU. So both these words are very similar. We can summarise that a multi-core is cores stored on one chip. They share cache, but we know that it doesn't necessarily mean faster. Whereas parallel processing might be several cores in a CPU or more than one CPU. That might mean we have a CPU and a GPU where we share the instructions across the CPUs or the cores. Again, this has got a similar aim to speed up the overall application.